Okay, in this video we're going to talk about something called the constant differences method, and we're also going to look at the different forms of a quadratic polynomial. Now, in this example here we have three different tables of xy values, and we're told this table of values represents a linear function, a quadratic function, and a cubic function. Now, remember before if we were given a table of data and we were trying to determine if it represented a linear function, we would first calculate all of our delta x values. So in this case, 3 minus 2 is 1, 4 minus 3 is 1, that's 1, that's 1, and that's 1. And then we calculate all our delta y values. So 13 minus 10 is 3, 16 minus 13 is 3, 19 minus 16 is 3. All of these are 3. And since we remember the definition of a linear function means that all of the delta y over delta x values, or the rate of change is always constant for a linear function, then that's how we would know that that represents a linear function. Well, if we have a quadratic function, which is what we're told these data represent a quadratic function, we can do something similar to see if in fact we have a quadratic function. And first I'm going to do my delta x's, and in this case each one of my delta x values turns out to be 0.1. So just like over here, all of my delta x's are the same. Well, if I take a look at my delta y values, 2.88 minus 1.88, that gives me 1. 3.92 minus 2.88, however, does not give me 1. That's going to give me 1.04. So right away I can see I don't have a linear function. 5.00 minus 3.92 gives me 1.08. 6.12 minus 5, that gives me 1.12. And this gives me 1.16. All right, so I can tell that this is not going to be a linear function. That is, it's not going to be a first degree polynomial because my differences here, my delta y's, are not constant. So I don't have a constant rate of change here. So it's not a first degree polynomial. However, I can check to see if it's going to be a second degree polynomial. And the way I do that is I basically do this same thing again. That is, I take the difference between each of these set of differences. So in other words, 1.04 and 1, that was the difference between these values of y. Well, now I'm going to take the difference between these two differences. 1.04 minus 1 is 0.04. 1.08 minus 0.04 is also 0.04. 1.12 minus 1.08 is also 0.04. And 1.16 minus 1.12 is also 0.104. So since this second round of differences comes out to be constant, that's how I know that this is a second degree or quadratic equation, because all of my differences came out to be constant. Well, I've got a cubic equation, and you can probably predict what's going to happen. First I check to make sure that all my delta x values are the same, and they are. They're all 5. Then I'm going to do the same thing that I did over here, which is I'm going to first check out my delta y's and confirm that I don't have a first degree polynomial. So let's see. Negative 5 minus negative 57.5 is 52.5. Negative 2.5 minus negative 5, that's 2.5. 25 minus negative 2.5 is 27.5. 152.5 minus 25 is 127.5. And 455 minus 152.5, 302.5. And as expected, I do not have a linear function. I don't have a first degree function. Well, let's do it again and see if I'm going to get a second degree function. 2.5 minus 52.5 is negative 50. 27.5 minus 2.5 is 25. 127.5 minus 27.5 is 100. And 302.5 minus 127.5 is 175. Well, these differences are not constant, so I don't have a second degree polynomial. However, if I do it one more time, 25 minus negative 50 gives me 75. 100 minus 25 gives me 75. And 175 minus 100 gives me 75. And these differences are constant, which tells me that I have a third degree polynomial or a cubic polynomial. So I can use this method of what we call constant differences, to determine the degree of a polynomial if I'm given a table of xy values. Now we're going to talk about the three forms of a quadratic polynomial. And remember, a quadratic polynomial is sometimes also called a second degree polynomial. And it's also sometimes just referred to as a parabola, since that's the shape of the graph that a quadratic polynomial makes. And there are three different forms of a quadratic polynomial. The general form, or the standard form, looks like this. Y equals ax squared plus bx plus c, where a, b, and c are some constants. The factored form we've looked at also is a times x minus r1 times x minus r2. And we've already seen this factored form with polynomials of any degree. And for a quadratic polynomial, since I know I'm only going to have two roots because it's a second degree equation, then I'm just going to have x minus r1 times x minus r2. And finally, the vertex form. The vertex form looks like this. Y equals a times x minus h quantity squared plus k. And for this form, the reason it's called vertex form is because this point h comma k, in other words, the point defined by this number and this number, h comma k, is the vertex of the parabola. In other words, if we were to graph a quadratic equation, then it would have a vertex somewhere, and this point right here, the vertex, that point is given by these coordinates h, k. All right. Notice the signs in front of the h and k. Those are important, as we're about to see in a minute. I've got x minus the h value, which is the x coordinate of the vertex, and I've got plus the k value, which is the y coordinate of the vertex. So those signs are going to be important. All right, let's take a look at these examples here. Example number 1, it says state the vertex of each quadratic polynomial. So I noticed that for each of these three examples here, they are already, these polynomials are already in vertex form. So this one, it's in this form, y equals x minus h quantity squared plus k. Well, for this one, all I need to do is read off these values here to find out what the vertex is. The vertex of this one is just the point 2, 3. It's in this form, x minus h quantity squared plus k. That's my h value, that's my k value. I just write them down, and that's the vertex. This one is a little bit trickier because notice that even though it's in this form, a times this quantity squared, my signs aren't quite right. So in fact, before I write down the vertex, let me rewrite this. Let me change this around just a little bit so that this is x minus a number. And so if I'm going to make this, to make sure I don't change anything, I'm going to write this as x minus negative 4 quantity squared plus negative 2. Now I've got it in this form, a times x minus h plus k. Now I can see my vertex is going to be this value and this value, negative 4, comma, negative 2. Those are the coordinates of my vertex. This one, example C, it's almost in that form, except I've got this constant is the first term, and I would like for it to be the last term. Well, that's easy enough to fix. I just need to take this and move it over to this side. My negative sign here is going to stay with this term, negative 2 times x minus 5 quantity squared plus 4. So just by rearranging those terms, I've got it in my vertex form, a times x minus h quantity squared plus k. And again, my signs here are correct. I've got a negative sign here, I've got a positive sign here. So my vertex for this parabola is going to be x minus, oops, not negative, x minus h, which is 5, plus k, which is 4. So those are the coordinates of the vertex for this parabola. All right, example 2, it says, rewrite each of the quadratics in standard form. Well, to put it in standard form, which is this form here, I'm going to need to multiply out my parentheses. I'm going to have to rewrite it without my parentheses. So, for this one, to rewrite it without the parentheses just means I'm going to take x minus 2 and square that quantity. So let me write that as x minus 2 times x minus 2, that's x minus 2 squared, plus 3. Now I just need to use my FOIL method and multiply out these two binomials. So let's see, x times x is x squared, negative 2x, and negative 2x is going to give me negative 4x. Negative 2 times negative 2 gives me positive 4. And then here's my plus 3. Now if I collect up all my like terms, which are just these two constant values, I get x squared minus 4x plus 7. And here I've got my equation now in standard form. Now the other two examples here, examples B and C, they are similar. They just involve doing a little bit of algebra and multiplying out a squared binomial. I'm going to leave those for you to do. And let's take a look now at example number 3. Example 3 says write the equation of the parabola that has the given vertex and passes through the given point. Okay, so I've got a parabola that is a second degree equation. It passes through, it gives me the vertex, the coordinates of the vertex, and tells me it passes through this point. Well, since I'm given the vertex, it kind of makes sense for me to use the vertex form of my equation of a quadratic, which is y equals a times x minus h quantity squared plus k. So let me start by taking my coordinates from our vertex and plug them into my form of my equation here. So y equals a times, my vertex is 3, 2, so x minus 3 quantity squared plus 2 is my y coordinate. Okay. Now, I know everything about my equation except for this value a. And now, hopefully this is starting to look kind of familiar because we're going to do the same thing in this case to find the value of a. We're going to do the same thing that we did before when we were trying to find, when we had our equations in factored form, our polynomials in factored form. Remember, to find the final equation of a polynomial in factored form, once we got all of our roots, all of our factors down, we had to take a point that was on the polynomial and plug that in and solve it for a. That's what we're going to do here. We're going to take this point, and remember this point is an x and y coordinate, 5 and negative 4. We're going to take this point and plug it in here and then solve for the value a. So if I plug in these two coordinates, this is my x coordinate, this is my y coordinate, plug that into here, then I will have y, my y coordinate is negative 4, y equals a times my x coordinate is 5 minus 3 quantity squared plus 2. Now I have an equation and it has just one unknown that I can solve for, my value for a. So let me solve this equation for a. Negative 4, let's see, a, 5 minus 3 is 2, quantity squared plus 2. Negative 4 equals a times 2 squared is 4 plus 2. Actually, let me rewrite that. Negative 4 equals 4a plus 2. That's a little more standard. Now let's see, I want to get all of my constant terms together, so I want to subtract 2 from both sides. That gives me negative 6 equals 4a, and those go away. I divide both sides by 4, and I get a equals negative 6 over 4, and if I reduce that, then a is negative 3 over 2. Well, now I have my value for a, and I can plug that in to my equation here, and I will have my completed equation, which is going to be y equals a, which is negative 3 halves, times x minus 3 quantity squared plus 2. And there is the equation of the parabola with this vertex, 3, 2, and it passes through the point 5, negative 4. Now you have a couple of other examples in your notes. I'm going to leave those for you to do on your own, and we'll take a look at these tomorrow in class.